you ever wondered how your smartphone turns the sound of your voice into digital data, or how a medical device converts a heartbeat signal into numbers a computer can analyze? That's the magic of analog to digital converters, or ADCs. These essential devices bridge the analog world we live in with the digital realm of computers. Today, we're exploring the main types of ADCs, their workings, pros, cons, and application. Let's dive in and discover how these tiny components make modern technology possible, from music apps to medical monitors. ADCs convert continuous analog signals like voltage from a sensor into digital numbers that computers can process. Imagine a thermometer measuring temperature. The analog signal is the actual temperature, and the AC turns it into a digital value displayed on your screen. Key specifications of ADCs include resolution, which tells you how finely the signal is measured, speed, which is how many samples per second it can process, and accuracy, which is how close the digital output matches the real signal. Understanding these basics helps us appreciate why different ADC types exist. Not all ACs are created equal. Depending on the application, you might need an AC that's super fast, extremely accurate, or very power efficient. For example, audio recording needs high resolution for clear sound, while a radar system might need lightning-fast conversions. That's why engineers have developed several types of ADCs, each with its own strengths and weaknesses. In the next scenes, we'll break down the main types and see where each one shines. Start with the successive approximation register, or SAR ADC. This type is one of the most popular in electronics today. SAR ADCs work by guessing the digital value step by step, getting closer to the actual signal with each step. Think of it like playing a game of hot and cold, narrowing down the answer. SAR ADCs offer a great balance between speed, accuracy, and power consumption, making them ideal for battery-powered devices and general-purpose applications. SAR ADC uses a binary search algorithm to find the closest digital value to the input signal. It starts by comparing the input to reference voltage, then adjusts its guess bit by bit. Each step halves the difference, quickly zeroing in on the correct value. This method is efficient and reliable, which is why SAR ADCs are found in everything from digital thermometers to industrial sensors. Their moderate speed and low power needs make them a go-to choice for many engineers. SAR ADCs are loved for their efficiency and versatility. They're fast enough for most applications and don't drain much power. However, they're not the fastest option out there, and their resolution is usually limited to around 12 to 16 bits. For ultra-high-speed or ultra-high-resolution needs, other AC types might be better. Still, for everyday electronics, SAR ADCs are a solid choice. Next up is the Flash ADC, known for its incredible speed. Flash ADCs use a bank of comparators to instantly convert an analog signal to digital in a single step. This makes them the fastest type of ADC, perfect for applications like digital oscilloscopes, radar, and high-speed data acquisition. The trade-off: Flash ADCs use a lot of power and take up more space, so they're not ideal for portable or low-power devices. Flash ADC works by comparing the input voltage to a set of reference voltages all at once. Each comparator outputs a signal, and a logic circuit quickly determines the digital value. This parallel approach means there's almost no delay, making Flash ADCs the go-to for applications where speed is everything. However, the number of comparators doubles with each extra bit of resolution, so complexity and power use rise quickly. Flash ADCs are unbeatable for speed, but they come with some drawbacks. Their power consumption is high and they require a lot of components, especially as you increase resolution. This makes them expensive and bulky for high-resolution needs. Still, for high-speed applications like video or radar, Flash ADCs are the top choice. Now let's talk about the Sigma Delta ADC. This type is famous for its high resolution and accuracy, making it perfect for audio and scientific measurements. Sigma Delta ADCs work by oversampling the input signal and using digital filtering to produce a precise digital output. They're slower than Flash or SAR ADCs, but their accuracy is hard to beat, especially for low-frequency signal. Sigma Delta ADC oversamples the input signal, meaning it takes many measurements per second. It then uses a process called noise shaping to push errors out of the frequency range of interest. Finally, a digital filter cleans up the signal, resulting in a highly accurate digital output. This makes Sigma Delta ADCs ideal for applications like digital audio recording, where precision matters more than speed. Sigma Delta ADCs are prized for their accuracy and ability to handle low-frequency signals with minimal noise. However, their conversion speed is relatively slow, making them less suitable for high-speed applications. They're also more complex in design, but for audio, instrumentation, and precision measurement, they're often the best choice. Pipeline ADCs offer a great compromise between speed and resolution. They're commonly used in applications like video processing and communications, where both high speed and good accuracy are needed. Pipeline ADCs break the conversion process into stages, with each stage handling a part of the signal. This allows for fast, continuous conversions without sacrificing too much accuracy. Pipeline ADC splits the analog-to-digital conversion into several steps or stages. Each stage processes part of the signal and passes the remainder to the next. This pipelined approach allows the ADC to process new inputs while previous ones are still being converted, resulting in high throughput. Pipeline ADCs are a popular choice for high-speed, moderate accuracy tasks like digital cameras and wireless receivers. Pipeline ADCs are valued for their ability to handle high-speed signals with decent resolution. They're not as accurate as Sigma Delta ADCs or as fast as Flash ADCs, but they strike a good balance for many real-world applications. The main drawbacks are increased complexity and potential for small errors between stages, but for video and communication systems, they're often the perfect fit. Integrating ADCs, also known as dual-slope or multi-slope ADCs, are designed for precision measurements over longer periods. They work by integrating or summing the input signal over time and then measuring how long it takes to return to zero. This method is highly immune to noise and is commonly used in digital voltmeters and other laboratory instruments. Integrating ACT charges a capacitor with the input signal for a fixed period, then discharges it with a reference voltage. The time it takes to return to zero is measured and converted to a digital value. This approach averages out noise and provides very accurate readings, especially for slow-changing signals. That's why integrating ADCs are trusted in precision lab equipment. Integrating ADCs excel at precision and noise rejection, making them ideal for laboratory and industrial measurements. However, they're much slower than other types, so they're not suitable for fast-changing signals. If you need accuracy over speed, integrating ADCs are a great choice. Let's compare the main ACT types side by side. Flash ADCs are the fastest but use the most power. SAR ADCs are a good all-rounder, balancing speed and efficiency. Sigma Delta ADCs offer the highest resolution for low-frequency signals, while pipeline ADCs are great for high-speed, moderate accuracy needs. Integrating ADCs are best for precision measurements where speed isn't critical. Each type has its place, depending on your application. Selecting the right ADC depends on what matters most for your project. Need speed? Flash or pipeline ADCs might be best. Looking for accuracy? Sigma Delta or integrating ADCs are your friends. For most general uses, SAR ADCs offer a great balance. Always consider your application's needs before picking an ACT type. ADCs are everywhere in modern technology. Your smartphone uses them to process touch, sound, and images. Medical devices rely on ADCs to monitor vital signs. Even your car uses ADCs for engine control and safety systems. Without ADCs, much of today's digital world wouldn't function as we know it. In audio equipment, ADCs convert analog sound waves into digital signals for recording, processing, and playback. High-resolution ADCs are essential for capturing every detail in music and voice, ensuring clear, lifelike sound in everything from smartphones to professional studio gear. Medical devices use ADCs to turn analog signals from sensors like heartbeats or blood pressure into digital data that can be analyzed and displayed. This enables accurate monitoring and diagnosis, improving patient care and safety in hospitals and clinics worldwide. Modern vehicles are packed with sensors that rely on ADCs. From monitoring engine performance to enabling advanced driver assistance systems, ADCs help ensure your car runs smoothly and safely. They're a key part of the automotive electronics revolution. Factories and industrial plants use ADCs to monitor and control processes. Sensors measure temperature, pressure, and flow, and ADCs convert these signals for digital control systems. This enables precise automation, boosting efficiency and safety in manufacturing. In communications, ADCs are vital for converting analog signals from antennas into digital data for processing. This is essential for everything from cell phones to satellite links, enabling fast, reliable data transmission in our connected world. Resolution is a crucial ACT specification. It's measured in bits and determines how finely the analog signal is divided. Higher resolution means more precise digital representation. For example, a 12-bit ADC can represent 4096 levels, while a 16-bit ADC can represent 65,536 levels. This matters for applications where detail is important. Sampling rate or speed tells you how many times per second the ACT measures the analog signal. It's measured in samples per second (SPS) or Hertz (Hz). Higher sampling rates are needed for fast-changing signals like audio or video, while slower rates are fine for things like temperature sensors. Accuracy measures how close the ADC's digital output is to the actual analog input. It's affected by factors like noise, nonlinearity, and offset errors. High accuracy is critical in scientific and medical applications where even small errors can make a big difference. Latency is the delay between when an analog signal is received and when the digital output is available. Some ACTs, like Flash, have almost no latency, while others, like Sigma Delta, may introduce a delay due to filtering. Latency matters in real-time systems where quick response is needed. Power consumption is especially important for battery-powered devices. Some ACTs, like SAR, are designed to use minimal power, while others, like Flash, consume much more. Choosing the right ACT can help extend battery life and reduce heat in your device. Noise is unwanted variation in the signal that can affect ADC accuracy. Some ADC types, like Sigma Delta and integrating, are better at rejecting noise. Understanding noise performance is key for applications where signal clarity is critical. ADCs have come a long way since their invention. Early ADCs were bulky and slow, but advances in semiconductor technology have made them faster, smaller, and more efficient. Today's ACTs are found in everything from tiny wearables to massive industrial systems, powering the digital revolution. The future of ADCs is exciting. As technology advances, we'll see even faster, more accurate, and more energy-efficient ADCs. Innovations like AI-driven calibration and integration with wireless systems are on the horizon, opening up new possibilities for smart devices and the Internet of Things. The Internet of Things, IoT, relies heavily on ADCs. Billions of sensors around the world use ADCs to convert real-world data into digital information for smart homes, cities, and industries. As IoT grows, the demand for efficient, reliable ADCs will only increase. Wearable devices like fitness trackers and smartwatches use ADCs to monitor heart rate, movement, and more. These ADCs must be small, low power, and accurate to provide reliable health and activity data throughout the day. Robots use ADCs to process information from sensors, allowing them to see, touch, and interact with their environment. High-speed, accurate ADCs are essential for robotics, enabling precise control and real-time decision-making. Scientific instruments depend on ADCs to capture and analyze data from experiments. Whether it's measuring tiny voltage changes or recording seismic activity, ADCs provide the digital data scientists need to make discoveries and advance knowledge. From TVs to gaming consoles, ADCs are at the heart of many consumer electronics. They help process video, audio, and user inputs, ensuring smooth, responsive experiences for users everywhere. Environmental monitoring systems use ADCs to track air quality, water levels, and weather conditions. These systems help keep communities safe and informed, providing critical data for decision makers and researchers. Aerospace systems use ADCs for navigation, communication, and control. High-reliability ADCs are essential for aircraft and spacecraft where performance and safety are paramount. Security systems use ADCs to process signals from cameras, microphones, and sensors. Fast, accurate ADCs help detect threats and keep people and property safe, whether in homes, businesses, or public spaces. Test and measurement equipment like oscilloscopes and multimeters rely on ADCs to digitize signals for analysis. The quality of the ADC directly affects the accuracy and usefulness of these tools for engineers and technicians. Smart home devices use ADCs to interpret signals from sensors such as temperature, light, and motion. This allows for automation and control, making homes more comfortable, secure, and energy efficient. Analog-to-digital converters are the unsung heroes of modern electronics, quietly translating the analog world into digital data we can use and understand. Whether you're listening to music, driving a car, or monitoring your health, ADCs are working behind the scenes. By understanding the different types and their strengths, you can better appreciate the technology that powers our digital lives.